Thank you. And now it's my pleasure and honor to introduce Professor Gerard Vignoles from the University of Bordeaux. Professor Vignoles gained he graduated from the École Normale Supérieure in Paris. Then he obtained his master degree at the University of Paris, after which he changed to the University of Bordeaux, where he obtained his PhD. And there he attained a post as an assistant professor at the Laboratory of Thermostructural Composites. And now he is there full professor at the University of Bordeaux. At the same time, he's the head of the joint research unit of the University of Bordeaux, the CNRS, the CEA, and the group Safran, as I read correctly, and his. He's also a head of the CNRS research, national research group on composites, ceramics. His main interests are image-based, multi-scale and multi-physics modeling of ceramic and matrix composites. So the stage is up to you, Gerard. So welcome.
Thank you, Mr. Chairman, for the very, very nice introduction. Indeed, thank you all for attending this talk. I'm quite happy to have so many people attending something that's not about petroleum or groundwater. So I'll be trying to give you some insight of how paramedia science and modeling in general can be helpful for the control of ceramic matrix composite processing. So it's about material processing here. I belong to that laboratory for thermal structural composites, which gathers 35 years of existence. And it's a joint unit of academic partners, the CNRS and the Bordeaux University, together with the CEA, the Atomic Energy Commission, and Safran Group. And well, the idea is that we work with high temperature structural materials, which are very high level materials applied in space technology, aviation, energy technology, industry, and to have a better integration of those specific materials and a good design with the very good performance to cost ratio. There's some need for research innovation. There's also some need for expertise and training the future ceramics engineers. Thermostructural composites, what are they? They have ceramic fibers as a reinforcement. So it's about fibrous media, sorry, no grains here. These look like what you know as the usual composite materials, like the carbon reinforced polymers, but in this case, you don't have a polymer matrix, you have a ceramic matrix, which is brittle and brittle like the fibers. So every component is brittle, but the result is not necessarily brittle, because if you tune nice interface between fibers and matrix, you can have something like delayed fracture, as you can see in the middle, in which the fracture facies is looking like wood. And these materials are non-brittle, but they are stiff and they are refractory. They can work at very high temperatures. The current applications range space propulsion, brakes for aviation, racing cars, thermal protection system for atmospheric reentry, ionic propulsion, industry. You have here, for example, bowls for a single silicon crystal pulling. And future applications are essentially in aircraft propulsion, also as a nuclear fuel cladding and other energy application. This is the spectrum of the applications. And of course, you can range from a few minutes of use at 3000 degrees down to a century of use at 100 degrees. And of course, in the middle, you find, for example, the cellular craft propulsion, which is a very promising market, which would be something like 1 year to 10 years for the lifetime of a part at 1400 degrees. So these CMCs started with very restricted applications, specifically spatial and military, but now the market is growing, for example, with aircraft brakes and aircraft propulsion. And they have very promising perspectives because these materials do not depend essentially on conflict minerals, as opposed to, for example, cobalt, chromium, nickel, etc. They are very compatible with hydrogen combustion, so this is very promising for aircraft propulsion. They have very good creep resistance as opposed to many metals. They are very lightweight, something like twice as light as many metals. They also are resistant to neutrons, so new applications are looked for, especially, for example, in heavy industry, in which there are wide possibilities opening. And this is why this national research group on ceramic matrix composites has been established since 2019. It collects companies which are interested in the use and production of these materials, but also research. And not only CNRS, but also CAA, ONERA, which is the aerospace agency, etc. Agencies like the Nuclear Waste Disposal Agency and the Army agency are interested. This is a map of all those stakeholders, and well, this shows that there's a great level of activity in this domain right now. Another topic is reinforced ceramic foams. In the same lab, we've been working on them. These, for example, have known large interest for heat exchangers, and are currently being developed for example, concentrated solar power receptors, and also for industrial heat exchange more in general. These are very porous structures, but chemical vapor infiltration, which is the process I'll be talking about, is a possible very interesting element for the processing route of these materials. Just to give you an example of a recent production from my lab, we went from the numerical design of a Gerard-like structure that has been first 3D printed by fusion deposition modeling and porous polymer state. Right after it's been impregnated with a pre-ceramic polymer and pyrolyzed. And the last step was to add a chemical vapor infiltration coating. And as you can see in the slice in the bottom, you have that the CVI coating gives a very good oxidation tightness to the ceramic, and also increases a lot the compressive modulus and strength of this ceramic foam. So it's been even patented. And I'm stuck. I'm pressing next and I don't have anything. Why is it so?
Yeah.
I think. Am I going to give the rest of my talk just with that image?
Okay, I will go for help.
Is there anybody from? Oh yeah, here we are. Okay. I was just thinking a lot. Don't know why.
Okay, fine.
Okay, what is the chemical vapor infiltration process? It's like this. You have a furnace, a reactor chamber in which you allow precursor gases. For example, if you want to deposit carbon, you just put hydrocarbon mixtures inside, plus hydrogen, argon, and dilution gases. Then you have your porous medium in the middle here, which is heated by different means, and then the gases will enter. Oh yes, now it's moving without my authorization. So the gases enter the porous medium, and then they are subject to pyrolysis, and in the end, they will react with the porous medium surface. They will leave a solid deposit, so you will have growth of the solid, and there are some byproducts, some gaseous byproducts that are evacuated from this medium to the outlet. This is an example of a carbon fiber preform. It can be very complicated. You have woven fabrics, but you also may alternate them with felts, which are non-woven, and you can have some needle punching of all that, so it makes them a very complex fibrous medium. So the motivations here are that these materials are extremely expensive in their fabrication, so optimizing the production is very important for the industrials, of course, and you want to lower the costs. But the performances should be guaranteed, and in particular, we will see the deposit uniformity. There's some pertinence of having a very good numerical simulation that has been consistently validated with respect to experiments. And when you have that, you can also prospect for alternative processes. So these slides summarizes many years of work in which in my lab we developed a multi-physics and multi-scale approach to chemical vapor infiltration. In the first block, we worked on the homogeneous kinetics of hydrocarbon decomposition, so that we could identify what are the exact species that are going to react with the surface and leave this carbon deposit. In the second block, we have also performed CFD analysis of the furnace, the reactor with the porous medium inside, without any detail on the porous medium. But if you do so with a flat medium, then you may have access to the heterogeneous kinetic rates. Now, if you merge that with the homogeneous, you got a full chemistry package. But of course, what is important is also to provide all the mass and heat transfer in the porous medium. So the third block is image-based modeling of heat and mass transfer, so that you can have all those properties at several stages of infiltration. And all that is merged together in, for example, finite element simulation of the whole material. And this gives you a distribution of the deposition rate, of the infiltration degree, the degree of pore filling, if you want, and also of the precise nature of the material as a function of time that can be compared to actual experiments carried out in our very lab. So we could validate this whole approach. I will give you some more insight in our work on structure to gas transport relationship. Well, this is very old work now, but we've been going to tomograph many years ago and had low res and high resolution scans of these porous media. And from those images, we could extract lots of information. For example, the distribution of internal surface area as a function of porosity, and that are elements that we could relate to like fiber growth models and percolation models. And we could do the same, of course, for foams, which have been reinforced by CVI deposits here. And the other part of the modeling is to address gas transfer in these porous media. In this case, we have basically three types of possible gas transfer, which is diffusion, interdiffusion of gases, of different gases. You have viscous flow, which is the usual Darcy regime. And in the middle, you got the rarefied regime that's called Klinkenberg or Knudsen flow or whatever. So we have 3 transport modes and they are linked to each other. So we chose to study them all together, even though in most cases, for example, Darcy flow is not important in CVI. So you all know that we can boil down all the information on that if we make some kind of averaging of the transfer to 3-dimensional tortuosity factors, which compare the ideal pores to the actual pores, okay? But these tortuosity factors are not necessarily the same for all the transfer properties. So I developed a code on RenderWorks for the simulation of rarefied gases. It's very appropriate because it's like a natural idea that you have when you think of kinetic theory of gases. So in this RenderWorks, the good thing is that I don't know why I don't have anything. Excuse me. Oh, yeah, thank you.
It's okay. Should be.
Okay, it's willing. So, yes, RenderWorks are very convenient because you can work in very large images without any important memory overhead. So it's very practical for this. So we simulate here, depending on the density of these green triangle events from continuum diffusion down to Knudsen diffusion, very conveniently, with the representation of a binarized porous medium. And moreover, it's rather easy to simulate infiltration. The important infiltration parameters in dimension are 2-dimensionless numbers, which is the sticking probability, which is a kind of measure of the reaction to transfer ratio, and then the Knudsen number, which is the degree of gas rarefaction. And I don't know why it's okay. The pore diameter is very important, so it's related to the internal surface area, and of course, this is why I was already telling you about that sooner. And if you want to compute an effective transfer coefficient with RenderWorks, you have the choice between 2 methods. Probably there are other ones, but these 2 are very interesting. One can be like a steady state method in which you simulate like cold on the one side and hot on the other side, and you see the heat flux. Okay. If you do that, you divide the flux by the gradient, and then you have the effective coefficient in the given direction. And you have to repeat that 3 times for the 3 directions. But on the other hand, you can also use the transient method, which is the plane simulation of diffusion, and you just pay attention to the covariance matrix of the displacements of the walkers, and you got the full tensor at once. Of course, you have to wait because it's converging rather slowly with time and number of walkers, but it works pretty good. And the good news is that the average coefficient converges much more rapidly than the detailed concentration field inside the porous medium. So you have your average information some 10,000 times faster than all details on the concentration field. And also you may handle very easily non-periodic images. When you have periodic images, you have the problem of mismatch between the 2 opposite sides. You can try and solve that with symmetry, but in this case, you will align the principal direction and the reference axis, which you don't want. So you can also do that with a random walker. You just translate your walker, but you just move his position on the opposite face with a random number, and this is equivalent to an average periodicity boundary conditions, which is weaker than the usual periodicity boundary condition, and it's largely sufficient to have a good representation. So it solves lots of problems for the computation of equivalent properties in porous media images. And now we can also easily make infiltration. When you have a sticking event, you choose the closest fluid node and you will increase its grayscale level value. And then on the fly, you may retriangulate your area close to the event, and then you can have something that increases. So some results on slip flow. We've been recently going to a new campaign of determinations of slip flow coefficients in rarefied transfer from CT images. And well, our results are represented here in the region of 0.6 down to 0.1 porosity, which is, well, we tried to compare that to literature, and actually literature is mostly literature on filters. And the problem with filters is that it's not the same range of porosity, but what we could see is that our data was really in line with the known results on fibrous media. Moreover, we performed the experiments on the same materials that we have imaged, and we could see that there was a very good match between the actual and the simulated Knudsen diffusion coefficients, except with high porosity, because when you are with high porosity and the low CT scan definition, you are losing the details on the porous media. And very interestingly, there's a method that has been suggested by Johnson and Koplik many years ago, and then it has been reused by some colleagues. When you have a porous medium family, meaning that you're spanning a porosity range, it is possible to infer the viscous tortuosity as a function of the binary diffusion tortuosity, which is really interesting. We checked that again by comparing our results obtained with that turnaround with very rapid computations with random walks as compared to very cumbersome direct computations of Stokes to Darcy computations, and it works pretty well. And our data was really in line with the literature on flow through fibrous media that, for example, many people have developed in the context of resin transfer molding, etc. Moreover, we could correlate the tortuosity from one regime to the other regime, and it works even independently of the direction and of the type of porous medium. We, for example, used the calcarb, which is fibrous preform for TPS, and we obtained results that are completely in line with the other fibrous media we were using here. This is an example of local scale infiltration in which we have now the evolution of the porous medium. And for example, a very convenient way of following the infiltration is to follow the Thiel modulus, which is the reaction to diffusion ratio. And this modulus, of course, increases all the time because the available space for diffusion shrinks, whereas the internal surface for reaction increases. So this Thiel modulus increases all the time, and well, there's some prediction that you can have from simple growth from the fibers. And of course, when infiltration comes near to the end, you have percolation effects, which gives you, of course, some deviations from that. And very interestingly, we could make some reverse engineering of CVI. I mean, the industrials gave us some preforms at several stages of infiltration. We took the first one, which was the uninfiltrated one, and we made some infiltration simulations on it and tried to see how the relative Thiel modulus was increasing and compared that to the actual experimental data. We varied our two dimensionless numbers, and in the end, we can see that there is a set of dimensionless numbers that better matches the actual evolution of the porous medium. So we could backward identify that, for example, in this case, we were in rarefied regime and we had a very high temperature, meaning a high sticking probability. And well, actually, the engineers confirmed that that was really the case, low pressure, high temperature. We also developed a two-scale approach in which we obtained the very fine resolution data and inserted that into coarse representations of the porous media. And doing so, we could show that we could capture the actual evolution of the pore size distribution of this type of material. We took the image that you see in A, and we intentionally downgraded the resolution by a factor 25 to have the image of picture B here. Then we performed both infiltration simulations, and we compared the results in C and D, and we could see that actually the result was quite good. So it's very good for a change of scale here. So to summarize on that, we have validated numerical tools. We also know that other methods do exist for computations of transfer, etc. But in every case, we see that dimensionless numbers here are very important because they all are what we are interested in, competitions between transfer, reaction. And we can also study infiltrability, meaning that we can vary the initial structure of the porous medium and see how it gets by infiltration as a final porosity. And we also want to use machine learning because it's quite appropriate. You take starting images, you infiltrate a lot of them, and you see how you can relate the infiltrability to the structure of the medium. Okay, now this was the first part, but I don't know how many minutes are left.
A few minutes.
A few minutes only. So I'll try to skip through some slides here. The second part is more at a larger scale. So CVI with thermal gradients. The problem of CVI, as I showed you so far, is that isothermal infiltration leads to premature pore plugging. So the idea is that you want to start infiltration from the pore end instead from the pore mouth. For that, if you introduce a correct thermal gradient, you can have it hot inside, cold outside. So in this case, where you have heat goes through the porous medium in one direction, and the chemical reaction is active in the hot part, and the precursor gas comes from the cold part. And then you have a dense zone, and you will shift the chemical reaction zone until you go to the pore mouth. Many variations of this CVI exist by contact with a hot susceptor, or with the circulation of electrical currents inside the carbon fibers, which are conductive. You can also use a radio frequency heating or microwaves, etc. You can also put that in a boiling precursor, for example, so that you can secure a cold boundary to the porous medium. Okay, so the modeling here would be to solve the balance equations, including heat equation, as opposed to what I showed you first. And also together with, of course, the gas species balance equation, the solid evolution equation, all that in multi-physics finite element solver. But it was also possible to derive some analytical models, which are very practical, because for all people, I guess, we don't want all the time to go to painful computations. So the principle for this analytical method is just to change frame, assuming that there's a front with a given velocity. And if you do so, you reduce your set to only a set of three ordinary differential equations. And if you do so, you can solve that and obtain a front existence criterion. In some cases, you don't have the front. In other cases, you have it, depending exactly on the dimensionless heat flux and the dimensionless mass flux. And very interestingly, this no front boundary obeys to the law of demand and offer. So the demand is what the chemical reaction wants in purple here, and the offer is what diffusion through the front can bring. And if the offer exceeds the demand, then you have a front. Otherwise, you don't. So this allows us to find that there exists a critical heat flux to have a correct inside-out infiltration. Yeah, we got the characteristic quantities of the front width, velocity, and all these quantities decrease when heat flux increases, and this matches experiments and previous models. So we have here something simple, but it has to be, of course, fed with equivalent transfer properties that we have already computed in the first part of this talk. I have 4 practical cases that I've been investigating during 20 years, more or less, which are either from the industry or from the lab. And I will already show you one here. This one was designed to make rocket nozzles. And there was an induction heating with radio frequency. So in this case, the first computation comes with the electromagnetism, and you can compute the vector potential. From this, you extract the Joule heating. Going backwards, sorry. Yes, here you are. We have the classical skin effect. But if you combine that with radiation, then you see that the temperature maximum is inside the material, which is what we want. We add the gas circulation here, which is quite rapid. And this further changes a bit the thermal gradients inside the material. And then we have a nice gradient, hot inside, cold outside. Then we can allow the gases to enter. I don't show you the movie because it doesn't work, but here is like a scheme of that. And in the beginning, you have, of course, what you want. Infiltration starts well in the center of the porous medium. And then the problem is that at some point, you see that there's some saturation effect, and you have some non-optimal infiltration zone inside the porous medium, whereas a nice infiltration front keeps on going and goes towards the preformed boundary. So I call that the Trilby hat effect, because you can see that the profile of infiltration looks like a Trilby hat. And the front criterion study applied to this particular case shows that indeed the actual heat flux that was applied to the material was below the critical flux in the conditions of the reference case. So we could see that the desired conditions for front were not met at the process start, and they are eventually met when you are shrinking the size of the preform and decreasing the hot side temperature. There's another case here. I don't know if I have time to discuss it. We are already done, more or less. Okay. So this one is with a boiling precursor, so that you have a very cold temperature on the boundary. And in that case, the numerical simulation matched very well the experiments, which are X-ray radiographs here with double transform. And we could see with the models, with the multiscale model, that depending on the value of the boiling temperature of the boiling temperature, you can go from the to the very good situation in which you have a nice front, to a bad situation in which you go back to the problem of isothermal infiltration. And in the middle, situation 2 is the Trilby hat again. So we could find that there exists indeed like an optimal gradient. And in fact, the study, the analytical study confirmed that this was working indeed with some very porous initial material. But when my colleagues switched to another porous fibrous medium that was much denser, it was not okay, and they had not the correct infiltration situation. So I will skip the other two cases in which we have again a bad and a good situation, and I will go immediately to the conclusion here. So we could see that depending on the exact configuration of the process, we could have either a bad situation, which is the Trilby hat effect, or not, depending on the importance of the thermal gradient and also on the size of the porous medium that has to be infiltrated from the inside to the outside. And basically, when you got something small enough, then you're quite sure that you can have the correct situation. If you're larger, then it's a bit more difficult, and we know now that we can play with the outside, the hottest temperature down to have something that works better. So just to say that we can offer optimization guidelines with a mixture of multiscale multiphasic simulation on the one hand, and also of some simple analytical estimates on the other hand. And if we bundle all that together, then we can efficiently increase the optimization of this process. So what's next? Well, chemical vapor infiltration has also other variants. For example, we can pulse the gases in, out. We can also work with the actual texture of the porous medium, of the initial porous medium, and have it made in such a way that the residual porosity that you get in the end is as small as possible. And of course, I have been working a lot on deposition of carbon from hydrocarbons, but many other ceramics can be deposited. For example, silicon carbide from chlorosilanes. And this is currently being done in a Horizon 2020 project with many colleagues. And another outcome of these years of work is that we can try and valorize those tools in other areas like melt infiltration of molten metals in these ceramic fibers or carbon fibers, also self-propagating high temperature synthesis, etc. I would like to acknowledge many people from my lab, from the industrial partners, from other labs, especially in Bordeaux or outside. And well, of course, support from our industrial partners here and also from the French region Nouvelle-Aquitaine. So I'm very happy to answer any questions, but before that, I got announcements. If you like ceramic processing, you will find here 3 conferences in 2014 for which I'm advertising. One in Daytona Beach, USA in January, one in Budapest in 2024. I hope you'll be there. And the last one in Montreal, Canada in July. And also I'd like to advertise for the French InterPore chapter meeting, which is going to take place in October 2023 in, where is it? Rueil-Malmaison, and yeah, close to Paris, and Benoit is organizing it. So many thanks for your attention, and happy to answer any question.
Okay, so thank you for this excellent, complex presentation. Even if it was slightly longer than originally planned, but I hope you understand.
Sorry for that.
It's the last lecture for today, so I let it go. Are there any questions? Okay, question number 1.
I was wondering why you re-inject the work. Just if you don't memory blending to import the point. So why is it possible to perform the whole work?
Well, the actual idea is that I do not give any constraint on the time of the random walk, and I really wish to wait until convergence. So it happens that a random walk may get out of the image once, twice, 3 times, or even more. And this is the idea of homogenizing. So you have to be sure that your random walker anytime is walking in some copy of the image, okay? This is in the principle of homogenizing, okay? Well, by the way, the time convergence of your effective diffusion coefficient gives you also an idea of the size of the mask upon which you can define a representative volume element. This is one of the nice outcomes of it, because when you see that you have converged in time, you also know that you have converged in space and that you have worked long enough to have something effective. So it's really interesting for that. So for that, you have to ensure that your random walker works any time, so any length. And for that, it's better to implement something like a repetition of your image anywhere to pave your space with your initial pattern.
Okay. Any more questions? Yes.
I apologize. My question is a little bit naive. I don't know much about the subject. It would seem that you have solved all problems, or most problems that I'm talking about process. What is there left to do?
Okay. What is there left? It's in the perspectives here, for example. There are other variations of chemical vapor infiltration, in which, for example, we are not like letting gases enter and wait all your time and just let things occur. You can say, I inject the gases, then after a while, I just stop everything. I push the gas away and I re-enter them. That's very interesting, because in this case, the byproducts are evacuated and they do not hamper anymore the further diffusion of the reactants. So this one, for example, is more complicated and we still have to model it, okay? This is one of the examples of just studying variants of the process. The other thing is that we can also think of new chemical systems which are more complicated, in which the sequence of the homogeneous reactions before you have deposition are different. And this renders the deposition, the chemical kinetics in general much more nonlinear, much more complicated. So we also want to address the effect of these nonlinearities. This is another very interesting variant of the process. And I told about machine learning too, because the idea of having an optimally infiltrable medium is really interesting. So, well, we don't want to go exactly into Adrian Bejan's constructal theory, but it's a bit like this. The idea is that we have a modeling tool for infiltration. So we have starting points and we can vary the starting points as much as we want, okay? Then we machine learn all that and we can try and find some optimum, okay? This is still, for example, a perspective in which we are starting our work. So this, for example, is an outcome.
Okay. Any more question? Yeah, one more.
About the parameters for intelligence, I was just wondering why simplify pathway also about is it because it doesn't exist, yeah? Or
well, it would be computationally very expensive, of course, because yeah, we've been computing, you know, the homogeneous kinetics, we've been computing them for something like 35 species, 150 reactions. So it's already a lot. When you do CFD with like 40 degrees of freedom by node, it's a lot. It's the usual problem that many combustionists have. People who are working on gas cracking and reforming, for example, encounter these difficulties. And then in that case, you need absolutely some model reduction. And in this way, it was like, you know, machine learning was not there. So it was just human learning. And what we did was try and find some most appropriate chemical scheme that would be tractable and yet more or less capture the essentials of what's occurring. The transition between, for example, one type of carbon deposited to another carbon deposited, which corresponds to the transition between some dominant species in the gas phase. This, yes.
Okay. Any more questions? I hope not. Okay, so if not, then we can close this session. I thank you for your attendance and have a nice evening and hope to see you again tomorrow at some other presentations. Thank you.